What we saw in our last talk was the requirement to have the maximum possible lift to drag ratio. Now, how do we get a very large lift to drag ratio? Well, what we need to do is to reduce the drag of the aircraft. Now, in order to reduce the drag of the aircraft, the easiest thing to do is to break down the total drag into its components. Then we look at each individual component in turn and look at how we can reduce each of the individual components. So if we look at an aircraft, the total drag of an aircraft is broken down into two main types: the lift dependent or induced drag and the lift independent or parasite drag. Now, the lift independent drag has lots of different types: skin friction, interference, cooling, profile, wave, base, trim and form. Now, these are for a powered aircraft, and for us there's some parts of this drag that we don't need to consider. We don't need to consider base drag. Base drag is for the bluff back end of an object. Wave drag, well, that's the effect of shock waves, so that's if we're flying transonically, supersonically, which we won't be in a glider, so we don't need to consider that. Cooling drag is the drag due to the installation of the engine, and we're going to consider pure gliders, so again we don't need to worry about cooling drag. So the only drag we need to consider for a glider is the lift dependent drag, induced drag, and the lift independent drag, form drag, pressure drag, trim drag due to our stabilizing surfaces, the interference drag where wings and fuselages meet, and skin friction drag, which is drag due to the presence of the boundary layer. Now, what we're going to do is we're going to look at these two types independent. Now, the lift dependent or induced drag is caused because our wing is creating a lift force and our wing is three-dimensional. So on the top of a wing we have a low pressure, and on the bottom of the wing we have a high pressure. Now, flows try and move from high pressure to low pressure. So what will happen is that the flow underneath the wing will try and move round onto the top surface of the wing. And so if we were to plot the streamlines of the flow over the upper and lower surface of the wing, what we would see is on the lower surface of the wing, the streamlines tend to be flowing outwards, so the flow's trying to move towards the tip, and on the top surface of the wing, the streamlines tend to be flowing towards the root of the wing. And if I look at the back end of the wing, at the rear of the wing, what we would see is that the flow coming off the bottom of the wing is moving towards the wing tip, and the flow off the top of the wing is moving towards the wing root. Now, what will happen is that these two sheets of flow moving in opposite direction from the bottom and the top surface of the wing will wind themselves up into two large counter-rotating vortices. Now, these counter-rotating vortices create a large downwash behind the wing, and we can see these vortices if something visualizes them. So what we see here is smoke in a wind tunnel and an aircraft flying through it, and we can see the two large trailing vortices created behind the wing and the large downwash being created. With this C-130 we can see flares being dispensed, and in the smoke behind it we can again see these pair of vortices being generated. If we have a particularly humid atmosphere, then in the center of these vortices where there's a low pressure we can see water vapor condensing out, and here we can see vortices, or the core of the vortex, streaming off from the wingtip of this DC-10. Any lifting surface will generate a trailing vortex, and so what we can see off of the tips of these propeller blades is again the core of the vortex being highlighted by the condensing of the atmospheric moisture. Now, the effect that these two trailing vortices have is that they affect the lift being generated by the wing. Now, normally if we have a two-dimensional wing without a trailing vortex system, the lift acts perpendicular to the free stream velocity vector, and again our lift force is equal to our weight. However, if we have a trailing vortex, then what happens is that the lift vector is pulled back, and so some part of the lift force is now acting against the direction of flight, and so part of our lift is now acting as if I have a drag. And I also need to fly at a slightly higher angle of attack in order to generate a little bit more lift to counter this effect. Now, how do we reduce induced drag? Well, there is a little equation that gives us our induced drag, and I don't want you to worry about it too much, but what this little equation tells us is that we get the minimum induced drag if the lift distribution, or how the lift is generated from tip to tip, forms an elliptic shape. Now, in order to generate an elliptic shaped lift distribution, what we can do is create an elliptically shaped wing. And that's why we see on a Spitfire and this Heinkel, they had an elliptically shaped wing. And the reason for that is it gives you the minimum induced drag. The problem is that creating these elliptically shaped wings is quite difficult. The opponent to the Spitfire, the Messerschmitt 109, had tapered wing, and a tapered wing generates something close to an elliptic lift distribution, but not quite. I think they said that the man hours required to generate this tapered wing on the ME 109 was about 1/4 of the time it took to generate the elliptic shaped wing on the Spitfire. So it's a trade-off. Your induced drag will not be quite as good, but you can make more of them in the same amount of time. And that's why we see most aircraft wings have taper. And the reason they have taper is to minimize this induced drag. If we look at gliders, they have taper. Quite often they have taper in a number of sections. And these tapering sections, again, try and mimic that elliptic lift distribution. Other ways that we can generate the elliptic lift distribution is by twisting the wing from the root to the tip. By reducing the angle of incidence from root to tip, we can change or reduce the amount of lift generated. And if we twist the wing in the correct manner, we can again get this approximation to the elliptic lift distribution. Another way we can reduce the induced drag is by putting winglets on, because what we have is that the flow is trying to get from underneath the wing to the top surface of the wing, and so if we put a blockage in the way, then it restricts the motion of the flow from the bottom to the top. It makes the tip vortices weaker, and if the tip vortices are weaker, the lift vector isn't pulled back as much, and therefore the induced drag is less. And it's not often you see a Formula 1 car without having end plates on any one of the lift producing surfaces, again to reduce the induced drag. Now, why don't all gliders have winglets? Well, this is an ASW 19, and we see the speed polar with and without winglets. And what we see here is that without winglets, the rate of sink is greater at lower speed than it is at higher speed when compared to a wing fitted with winglets. So at low speed, the winglets would reduce our rate of sink and therefore increase our endurance, but at high speed the winglets increase our rate of sink and therefore the winglets reduce our endurance. Also, if we look at that little equation for the induced drag, we see that the induced drag is inversely proportional to the aspect ratio, which is why we have wings with very high aspect ratios on gliders, because if we increase the aspect ratio, we reduce the induced drag. So again, try and get an elliptic lift distribution, put winglets on, and have a high aspect ratio, are all reducing the induced drag. And if we reduce our drag, we increase our lift to drag ratio. And we see in nature efforts to reduce induced drag. And if we look at this buzzard, we can see that the buzzard has splayed its primary feathers out of its wingtip and essentially turned a relatively low aspect ratio wing into multiple high aspect ratio wings, and again possibly there to break up the wingtip vortices. One of the things you'll see at Port Moat quite often is the geese flying in formation, V formation, over the airfield. Now why do they do this? Well, behind the wing there's downwash, and outside the wing there's upwash. Now, if we're flying in upwash in a glider, we like that because we stay up for longer. It's why we fly on the ridge. These birds are doing the same thing, but instead of a ridge, what they have is the upwash from the wing of the bird in front. So all of these birds are benefiting from the trailing vortices of the bird in front. And if you do the numbers, funnily enough, the guy on the front actually benefits from the two guys behind, because if they've got a downwash behind them, in front of them is an upwash, and therefore this bird is sitting in the upwash of these two birds. The other effect which we have from induced drag is the requirement to coordinate turns. Now when we turn an aircraft, what we do is we generate more lift on one wing and less lift on the other wing to generate a moment which rolls the aircraft and then turns it. But what we've seen is that if we generate lift, we generate an induced drag, and the more lift we generate, the higher the induced drag. And so when we turn the aircraft, we generate more lift and therefore more drag on the wing that's rising, and less lift and therefore less drag on the wing that's descending. And therefore, as the aircraft is rolled to the left, in this case to turn to the left, the increase in drag on the right hand wing causes the nose to yaw to the right, and we have what's known as adverse yaw. And we counter the adverse yaw with the rudder in order to coordinate the turn.